Hello everyone, I'm Sean from KTH Sweden, and today I'm presenting our paper with Michael Ankeler and Tino van Koof entitled Revisiting Accurate Geometry for Morse-Smale Complexes. So let's get started, let's briefly recap what is a Morse-Smale complex. Given a scalar field whose values are color encoded, red is for higher values and blue is for lower values. The points where the gradient becomes zeros are called critical points. And in 2D cases, there are three types of critical points: minimum, saddle, and maximum respectively. And integrating the streamlines starting at the saddle points in the direction of the eigenvectors gives us the separatrices. The separatrices together with the critical points give us the Morse-Smale complex. In the traditional continuous setting, the Morse-Smale complex can be challenging to compute in practice. To overcome this problem, one can use discrete Morse theory, first introduced by Robin Foreman. This version of Morse theory aims to describe the concepts and the properties of the continuous Morse theory, but in a combinatorial manner. Instead of working with the continuous scalar fields, we are now working with functions whose values are placed at the component of a grid, so that there are grid vertices, grid edges, and grid cells. And instead of computing the gradient at every point on the domain, we now compute the matching arms to describe the discrete gradient fields. And they can be thought of as arrows linking the vertices to the edges and edges to the cells. We can see that there are unmatched components on the grid. They are called critical cells, and based on the type of component they will be matched accordingly. Vertices are called minima, edges are saddles, and cells are called maxima. Together with the gradient fields, we can create the discrete Morse-Smale complex, and we can see here they are almost identical. So, how to compute discrete Morse-Smale complex? For our intention, we consider different scalar fields whose continuous Morse-Smale complex can be seen here. It describes a circular shape here, and there's another segment that goes into the bottom left corner. And remember that the discrete Morse-Smale complex aims to describe this using the matchings only. There are many proposals on this method, but the first probably correct methods were introduced by the group of Vanessa Robbins, and we call it steepest. And this is considered as the standard to extracting Morse-Smale complex nowadays. This algorithm works locally, dividing the grid into substructures called lower stars and working in there. So for instance, considering the grid cell here, the values of the vertices of this cell can be seen here. And this algorithm always matches the vertex 4 with the edge 4 one because it's the steepest descent direction. And the rest of the lower star will be matched from there. This results with the Morse-Smale complex, but with the undesirable geometry as the circular step cannot be seen here. Two groups work independently to overcome this problem. Their idea also based on the algorithm of the steep descent, so they also work on the lower star. But instead of always moving into the steep descent direction, they assign to the possible choices a weight and chose probabilistically. By doing this, we obtain a Morse-Smale complex with the geometry that is very close to the continuous counterpart. So this algorithm works efficiently to extract the discrete Morse-Smale complex, and the problem of inaccurate geometry has been solved. But the story doesn't end there. By not moving into the steep descent direction, we can produce Morse-Smale complexes which have different topology. For instance, here we use the two methods to extract the Morse-Smale complexes on a scalar field interpolated from a randomly generated small matrix. There are two separatrices which have different inconnectivity. They are colored red and yellow. The red one on the probabilistic method is connecting to a different maximum, and the yellow one is connecting to a different minimum. They are completely different topology. One can argue that we can overcome this problem using the topological simplification, but that is not the case either. We're considering here a very noisy data set, and we use the two algorithms to extract the Morse-Smale complex. and we've simplified them with a very high persistence threshold corresponding to 45% of the data range. And we can see that the problem still persists. The separatrices, the red one, on the steepest descent method is missing completely from the probabilities method, whereas the yellow separatrice is connecting to different minimum right now. The problem gets even worse when we are working with real dataset. Considering here a scalar field extracted from a total cloud variable of a time step of the Isabel hurricane dataset, and we only shown here the separatrices which have different inconnectivity between the probability method and the steep descent method. And we can see there's a lot of them, and in fact, around 10% of the separatrices have different connectivity. So we've shown that the steep descent method is mathematically proven. It produces Morse-Smale complex with consistent topology comparing to the continuous version, but also incorrect geometry as well. The probability chosen methods overcome the problem of incorrect geometry, but in the process of doing so, they also produce different topology of the Morse-Smale complex. So this leads us to a question whether if we can achieve both consistent topology comparing to the continuous version and correct geometry as well. We've seen that applying the steep descent method on a uniform grid gives us a bad geometry for the Morse-Smale complex. This is due to the limited choices during the computation of the matching. We either have the vertical or horizontal choice, which are demonstrated through the histogram of the grid iteration here. They are concentrated on a very few values, and this gives us a very bad geometry for the Morse-Smale complex. So a naive idea is to divide its grid cell into two smaller triangles, and we are adding one more direction into the possible choices. And the geometry is a little bit better now. It's a little bit rather for the Morse-Smale complex here, but it's still far from perfect. So we are moving into the irregular grid, whereas the vertices of this grid is placed randomly according to the Poisson distribution. And we use Delaunay triangulation to create this grid. Looking at the histogram of the grid iteration, we can see that the values are spread more evenly now. And this gives us the Morse-Smale complex grid have geometries that is very close to the continuous version. So our idea is that if you want to extract the Morse-Smale complex, if it's possible, then it's better to have the values placed on the vertices which have a high degree of freedom, for example, irregular grid. But it is not always possible to have that kind of grid in all applications. For most applications, they come with a predefined grid, and most of the time it is uniform grid. So if you want to extract the Morse-Smale complex on this kind of grid, it gives us bad geometry due to the lack of choices during the computation of matching. So our suggestion is to adding more information into the uniform grid. That means we adding one more vertices into the middle of the edges and one more vertices into the cell. The values of the new vertices will be linearly interpolated. And in a sense, we are covering the missing directions, but to a very extent. And this gives us the Morse-Smale complex with the geometry is really close to the continuous version. In conclusion, we showed that not moving into the steep descent direction can produce Morse-Smale complexes with different topology, and the differences happens in a lot of scenarios and cannot be removed by means of topological simplification. And we also show that the problem of inaccurate geometry of the steep descent method is due to the limited number of directions during the computation of the matching. So more optimized grid structures can allow the steep descent method to extract Morse-Smale complex with better geometry. And from the observations, we suggest a way to achieve a better Morse-Smale complex in terms of geometry while retaining the topology from the steep descent method. Our future work is consist of two things. The first one is investigating more on the method that found the category of accurate geometry and better optimize our method to have shorter completion time. That's it for my presentation. Thank you for listening.